All right, today we're diving into something really cool, Riemannian geometry, and this idea of understanding a world completely from within. It's a bit of a mind-bender, for sure.
So, let's start with a really fundamental question. Imagine you're an inhabitant of some surface, like a tiny ant on a giant beach ball. You can't fly off and look at it from space. So, how in the world could you figure out its shape? Is it flat? Is it a sphere? Something else entirely? This is the exact puzzle that Riemannian geometry was built to solve.
So this brings us to our first section, a world from within, the explorer's dilemma. And yeah, it really is a dilemma that forces a whole new way of thinking about geometry.
Okay, so normally when we think about the shape of something, like a sphere, we're using what's called an extrinsic view. We're floating in space looking at it. But our poor explorer, they're stuck with an intrinsic view. They're on the surface looking around. All they have are the tools right in front of them. They can measure distances, check angles, maybe see how the horizon curves away, but that's it. No bird's eye view.
And this is the core idea. Barrett O'Neill, who wrote the book we're drawing from for this, puts it perfectly. He says, roughly speaking, we study the geometry of a surface as seen by its inhabitants. That's the whole game right there. We're literally throwing away the crutch of seeing things from the outside and building a whole new kind of geometry from scratch, from the inside out.
All right, so if we're going to solve this explorer's problem, we're going to need a completely new set of tools, a new rulebook for geometry.
And the most fundamental concept in this new toolkit is something called a geometric surface. Now, that sounds fancy, but the idea is actually pretty intuitive. Imagine that at every single point on this surface, there's a little tiny flat plane, just touching it. That's the tangent plane. And on that tiny plane, there's a unique set of rules, an inner product, that tells you exactly how to measure lengths and angles right there. It's like every single spot on the surface comes with its own custom-made ruler and protractor.
And this is a total game changer, right? It means geometry isn't about what a shape looks like from the outside anymore. It's built entirely from the inside out. Everything our explorer needs to know, distance, angles, even the very bending of their world, is determined by these local rules that they can actually measure.
Okay, this brings us to the first and honestly the most powerful tool in our new kit. We're talking about curvature, but not like you've seen it before. This is an inside job.
What we're talking about is something called Gaussian curvature. See, the old way of thinking about curvature required you to be in 3D space looking at how a 2D surface bends. But Gaussian curvature, it's a number, a single value, that our explorer can calculate right where they're standing. It measures the intrinsic bending of their world with no cheating, no peeking from the outside. It's a property that belongs to the surface itself.
So when our explorer takes this measurement, what do they find? Well, it basically comes in three flavors. If they get a positive number, their world is bending like a sphere. If they get 0, well, it's flat, just like a plane. A cylinder is interesting because you can unroll it to be flat, so it also has 0 curvature intrinsically. And if they get a negative number, they're on something like a saddle or a Pringle chip, where the surface curves one way in one direction and the opposite way in another.
All right, next big question for our explorer. If your world is curved, what does it even mean to walk in a straight line?
The answer has a great name. It's called a geodesic. And the definition is actually super simple. A geodesic is a path where you have 0 acceleration. I mean, think about it. If you're driving a car and you want to go straight, you just hold the steering wheel steady. You don't turn left, you don't turn right, you're not accelerating sideways. A geodesic is just that principle, but applied to any kind of surface, flat or curved. It's the absolute straightest path you can possibly.
So let's try this out. Imagine you're our explorer, and you're standing on a sphere. You pick a spot, you choose a direction, and you just start walking. The only rule is, don't turn the steering wheel. Just go straight. What path do you trace? Well, you'd end up walking along what's called a great circle. This is the biggest circle you can draw on a sphere. And it's not just an abstract idea. This is exactly the path an airplane takes to fly from New York to Tokyo. It looks curved on a flat map, but it's the shortest, straightest possible route. It's a geodesic.
Okay, this is where it all comes together. Our explorer has the tools, they can measure curvature right where they stand, and they know what a straight line is. Now, they're ready to put it all together and make a truly mind-blowing discovery.
So here's the ultimate experiment. What if our explorer could somehow measure the Gaussian curvature at every single point on their world, and then add it all up? What would that one single number, the total curvature, actually tell them about their home? The answer is one of the most beautiful results in all of mathematics, the Gauss-Bonnet theorem. And what this theorem does is absolutely profound. It creates a direct link between geometry, all those local measurements of bending, and topology, which is the study of the overall fundamental shape of an object. Stuff like how many holes it has. It says that if you add up all the local curvature, the total is always directly tied to a topological number called the Euler characteristic.
And check this out. Here's the theorem in action. Take a sphere. No matter how big or small you make it, if you add up all its curvature, you always get 4 pi. And its topological Euler number is 2. Now look at a torus, a donut shape. It has parts that curve positively and parts that curve negatively. And you know what? They cancel out perfectly. The total curvature is always 0, matching its Euler number of 0. A double donut, always negative 4 pi. This is an unbreakable law. The local bending is locked to the global shape.
And this leads us to the big finale, the punchline of this whole story. As the book puts it, the curvature of a compact surface completely determines its topological structure. Think about what that means for our explorer. They can finally answer their question. They can add up all their local measurements, get a final number, and say, aha, the total curvature of my world is 4 pi, I don't need to see it from space, I know I'm living on a sphere. It's just an absolutely incredible achievement.
So you might be thinking, okay, that's a cool math puzzle, but what does it have to do with the real world? Well, the implications are cosmic.
So let's just recap the big ideas from our journey today. First, we learned that you can define geometry completely from the inside. Second, all those little local measurements of bending can actually tell you the global shape of your entire world. And third, a surface's geometry and its fundamental shape, its topology, are deeply, powerfully connected.
And why is this so important? Because this radical shift in thinking, this intrinsic viewpoint, is the absolute bedrock of modern physics. It's the exact mathematics Albert Einstein used for general relativity. In his theory, space-time isn't just a backdrop. It's a dynamic four-dimensional manifold, basically a higher dimensional version of the surfaces we've been talking about. And the curvature of that manifold? That's what we feel is gravity.
And that leaves us with one last, huge question to think about. The very same math our little 2D explorer used to figure out their world is what physicists use today to understand our four-dimensional universe. So what if we could do the same experiment? What if we could measure the overall curvature of our own universe? What would that tell us about its true shape and maybe even its ultimate fate?